SwayamPrabha. Digital India. Educated India.
In this lecture, we continue our discussion on basic concepts as well as the conservation equations. In this lecture, let us have a brief revision of vector calculus applicable to the governing equations of compressible flow, and then we will continue with the governing equations. As far as vector calculus is concerned, we would like to briefly discuss about gradient of a scalar, divergence of a vector field, and line, surface and volume integrals. To begin with, the gradient. You see, we have written an expression for gradient of P, and of course, in the fluid dynamics this letter P has a significant influence. We know it is pressure, and pressure is a scalar, but gradient of pressure is a vector quantity, because the gradient operator, when it operates on the scalar, turns it into a vector, which had also been briefly discussed when we were talking about the index notation in the previous lecture. So, we have the three components of the vector grad P, and we see that there is a pressure gradient which is a scalar associated with the respective unit vectors along the three directions, and these pressure gradients occur in the momentum equations of fluid flow. Whether you have viscous flow equations or inviscid, they will always be present. If you take modulus of the gradient of pressure, you get the maximum rate of change of pressure per unit length of the coordinate space. Now, you can also have a directional derivative of pressure. That means, you may like to know how the pressure is changing along a particular direction which you would like to define through a unit vector, let us say S, and that may not coincide with the Cartesian directions x, y and z. There is absolutely no issue. You can have a directional derivative where you dot the gradient of P with the S vector to get dP ds, which is the directional derivative of pressure. You may see that in fluid flows, the pressure changes in a particular region where you can have three sub regions like indicated as P1, P2, P3, and then P3 is greater than P2 is greater than P1, which basically indicates that as you move along the region, you move from lower to higher pressure or the other way around, and gradient of pressure would end up indicating the direction along which the pressure changes most rapidly. Let us look at divergence of a vector field. So, here we are talking about velocity, which is a very important vector field for us, and we would like to find out what is the divergence of V. V in general can be a function of x and y and z if it is a steady flow. Additionally, it can also be a function of time if it is an unsteady flow, but as far as the divergence operator is concerned, it just looks at its spatial variation. We also remember the del operator, it is I del del x plus j del del y k del del z, it should be del z here. We had used this operator in the previous slide as well, and then when we take a divergence of the velocity vector, then basically that operator is indicated here with its three components, and then it dots with the velocity vector, which has x, y and z components. You may write them as u, v and w also, and then when it is dotted it turns out to be like this. So, it is a dot product between two vectors, and then what it yields is basically a scalar. Coming to integrals, we handle a lot of integrals in fluid dynamics, line, surface and volume integrals. Let us say you have a closed curve which is indicated by C, and you are traversing that curve along, say, the counterclockwise direction. Then on that curve C, you may like to draw a small unit vector ds, and then you are also identifying the local velocity vector at the midpoint of that ds vector. So, that ds vector can be defined in this way, that you have the unit vector along that direction indicated as t, t stands for the tangential direction, times the scalar measure of that element, that can be the indication of ds vector. And then instead of an closed curve, you can also have a open curve between 2 points, let us say A and B. There too you can define a ds vector, and then when you take a line integral of the velocity vector, it can either be along the open curve, let us say we call it C in both cases, or a closed curve like we have shown over here. And then when we take the line integral in the case of an open curve, we keep this curve incomplete. We say we are integrating between the points A to B on an open curve, and we take a dot product between the velocity vector and the ds vector that we have already defined. While if we take it along the closed curve, we would indicate it with a closed curve written on the integral. It is not always possible to follow these nomenclatures very meticulously in terms of drawing a complete curve or an incomplete one, depending on the context that we are discussing. You have to always figure out what we really want to mean. Here we are trying to do it from a more basic level, trying to explain the implications, but when it comes to writing a large number of equations and things like that, we may not be in a position to meticulously mention all this every time. So, you have to be a little cautious and attentive to understand the context. Let us look at surface integrals. We can have surface integrals involving scalars as well as vectors. When it is an open surface, you cannot have shapes like this, like a cuboid or a sphere, but it is rather a planar surface like the one you can draw on this slide, on the plane of the slide, and then you can try to integrate a scalar or a vector on that. If you do so, then you try to indicate the integral in this form, where it is just a double integral in the sense it is a surface integral, and then the integrand is p, which is a scalar integrated over the surface area ds, which would of course yield a vector. If you on the other hand integrate a v dot ds, that ends up forming a scalar over this particular surface area. Similarly, if it is a cross product, it would end up forming a vector again on the open surface. Like you do it for an open surface, you could also do it on closed surfaces of this kind, like we have indicated, or very arbitrarily shaped closed surfaces. You can imagine that control volumes, when they are defined, could have very arbitrary shapes and sizes, and then you have to account for that entire control volume and consider integrating these quantities over the exposed surface, the outer surface of that control volume. And you when you are doing it on such a surface, you are saying it is a closed surface. There we use this nomenclature of a closed curve, which essentially means a closed surface. That means it envelops a volume inside it. Again, remember that There may be multiple occasions where we may not be able to indicate these symbols time and again, but once you get familiar with the concept, you should be able to interpret what it exactly means in a given context. Here we have integrated the scalar p over ds, and here we have done the dot product between v and ds, the cross product between v and ds. The outcomes are again vectors, scalars and vectors, like it was for the open surface. We move on to volume integral. Here we say that there is a particular volume which is kind of enveloped by the control volume that you are talking about. It is of course having a closed surface, and there are numerous infinitesimal control volumes inside that relatively big control volume V. And let us say you are integrating a scalar field rho, it could be density, and then you could have a volume integral indicated like this. The outcome of this integral of course will be a scalar. You can have a volume integral of a vector too. So, if you are integrating the velocity vector over that volume, that will yield you a vector, and you are indicating triple integrals here because it is volume, while in the previous slide we were using double integrals because it was area. We are interested very much about finding relations about line, surface and volume integrals. This is one of those very important theorems which gives a connection between line integral and surface integral. Here you are basically performing a line integral along a closed curve, and you are trying to correlate it with a surface integral over an open area or open surface. So, the line integral is a dot product between the vector v and ds, let us say the velocity and the elemental vector drawn along that curve. So, that gives you the dot product, that is equal to the surface integral of the curl of the velocity vector dotted with the surface vector. Remember that this is a lower case s, whereas this is an upper case s, and they have different contexts. The lower case indicates that you are along a line, the upper case indicates that you are on a surface, and they are often also associated with the vectors explicitly mentioned. Even if it is not mentioned, depending on the context you have to interpret whether it is a vector or not. So, this is a very important theorem called as the Stokes theorem connecting line integral and surface integral. Let us look at divergence theorem. When you have V dot ds, where ds is the area because it is uppercase S, and you are integrating over a closed surface, then that is equal to the volume integral of divergence of V over that particular control volume. The uppercase V over here has been used for indicating the velocity vector. The lowercase v has been used for indicating the volume, but again there could be equations where this dV is written as d capital V, and you have to interpret it as volume and not as a vector velocity. So, this is a very important theorem again connecting surface area integral with a volume integral. Then comes another important theorem, the gradient theorem, which connects the surface integral with a volume integral. Here we are integrating a scalar over the surface, and when you integrate it, what you get on the right hand side of the equation according to gradient theorem is that you have a gradient of the scalar integrated over the volume. So, let us say if the scalar is pressure, then pressure when integrated over the surface would end up giving you the volume integral of the gradient of pressure integrated over that particular volume, which is enveloped within the surface area. Therefore, these three theorems that we learnt about give us ample scope to move back and forth between different types of integrals: line, area and volume. Let us look at governing equations of fluid flow in a more generalized framework to begin with in the viscous domain, which are the famous Navier-Stokes equations. And we basically talk about conservation of mass, momentum and energy. The mass conservation is often called as the continuity equation also, and we have briefly had a look at this equation earlier in the previous lecture. You remember about these two terms A and B that we talked about, and now we see more terms coming up as we move on to the momentum equation and the energy equation. So, in the momentum equation you have four terms C, D, E and F, and you see some of them are surface integrals while others are volume. Though as I mentioned earlier, we may not be indicating the closed surfaces and so on every time, but you have to understand the context. Moving to the energy equations, you also have four terms there G, H, I and J. There too you can see surface integrals and volume integrals. Of course, as you can understand, since we are having these integrals, we are basically talking about the control volume approach. If we were to look at an infinitesimal fluid element, that means we were practically talking about the conservation equations as it applies at a point, then you would have differential forms of these equations. Now, to say a little bit more about some of the important terms here, you can see sigma ij, the stress tensor as we had mentioned earlier, which comprises of three different terms, and we would detail them later, but for now we are briefly mentioning that the first term has to do with pressure, which is the normal component of the stress, the second term with shear, and the third term with the bulk modulus or the volumetric stress. We will have a more detailed discussion about all this in subsequent lectures. If you look at the shear stress expression, then in general it can be represented in this manner: A plus B times within brackets del uy del xj plus del uj del xi the whole to the power of n. And for a Newtonian fluid, A equal to 0, n equal to 1 and B is equal to mu. And the E term that you have in the energy equation is comprised of the internal energy plus the kinetic part ui square by 2. Now, very briefly to mention over here, you could actually think about curves like this indicating the strain rate versus the shear stress, and then in a Newtonian fluid you see a linear variation between the strain rate and the shear stress, but depending on the kind of fluid that you are handling, you could have other kind of behavior where they are non-linear in nature. Basically, the index n would then decide how it works, and there could also be fluids which do not show any strain for a certain level of stress, beyond that yield stress it would start deforming. So, based on that, different kinds of behaviors are briefly shown in this figure, and this figure is taken from the very famous book Viscous Fluid Flow by F.M. White. Let us have a more detailed view of the momentum equation, which is basically the Newton's second law, the F equal to ma equation applied to a fluid control volume. And then you see basically that the terms C, D, E and F are detailed to a greater extent over here. The C term basically stands for net rate of momentum change inside the control volume. D stands for net momentum efflux through control surface. E stands for net surface force, and F stands for net body force. And then if you were to write this for an infinitesimal fluid element in the Eulerian framework, it would of course change to a derivative form, and then it would show up as we have indicated here below. You can see that there are time derivatives as well as spatial derivatives applying on the different effects that we are talking about. So, again you will have momentum change inside the control volume, momentum efflux, surface force and body forces, but this time applying for an infinitesimal fluid element. So, basically it acts at a point. Again, in these equations I hope you are taking note that there are indices associated with a lot of terms, some of which we have explained earlier. Again, there is some homework that you will have to do to understand further implications of this, and we will also try to elaborate from time to time wherever possible. Remember that as you move from a finite control volume Eulerian framework to an infinitesimal fluid element Eulerian framework, you would need the Gauss divergence theorem to be applied, and again it applies back and forth based on which formulation to which other you are moving. Let us have a brief look at the energy equation, which is basically the first law of thermodynamics expression. Here again you have four terms G, H, I and J. They indicate net rate of energy inside control volume. That is basically the time rate of change of the energy content. H indicates the net energy efflux through the control surface. I represents the work done by surface forces sigma ij, and J represents work done by heat transfer. So, we are talking about this first term, and the body force, which is the second term here. Again remember that these capital V's are to be interpreted in the sense of volume integrals, and again from a finite control volume Eulerian framework, if you move to an infinitesimal fluid element Eulerian framework, then the equation changes to a differential form. Again, instead of integrals you will see derivatives over here, and in both the forms you have indices being represented. So, you will actually have to recall the discussion that we had earlier on index notation, which has to be carefully applied term by term to understand the interpretation. As you can understand that the index notation basically gives a very compact or a compressed way of representing complex equations without breaking them down into multiple components and showing the elaborate expressions. With a very compressed expression you can show summation effects. Again remember to move back and forth between these two forms, you would like to use the Gauss divergence theorem. So, we come to the end of this lecture. In this lecture, a brief revision of vector calculus applicable to the governing equations of compressible flow was completed, and we continued with our further discussion of governing equations of compressible flow. Thank you.